Okay, so hello, good morning and good evening, everyone. It's really a great honor to have Dr. J. Famiglietti here today to give a presentation on global water cycle and water security. Before we start, I would like to spend a few minutes to give a brief introduction of Jay. I know many of you, knew him already. At least, many of you at least have heard of the famous name Famiglietti. Uh, Jay is the professor in the Department of Geography and Planning, also the executive director of the Global Institute for Water Security at the University of Saskatchewan. I don't know how to pronounce it, Saskatchewan, right? So I don't have the time to talk about his tremendous accomplishment. I will place a copy of his CV in the chat room later. Here is a very impressive Google Scholar matrix. You can tell with H index of 80 and over 26,000 citations so far. Jay and I have a long history of friendship. We came to UT at the exactly same time in the summer of 1994. I still remember we met each other the first time, but the difference was huge. Even though he was only a few years older than me, he came to UT as a junior faculty, and I was there as a senior PhD student. That was 8 years after finishing my bachelor degree from college. But anyway, he has been my teacher and a friend ever since, and we had many opportunities to collaborate in research over the years. Jay is truly a world-renowned hydrologist. He's also a pioneer in using GRACE and other remote sensing data to study the global water cycle. So now I will just give the floor to Jay. You have a 45 to 50 minutes of talk and followed by a QA section. But it's flexible. If you want more time, I think it's fine. Yeah.
Okay, sounds good.
Okay.
Let's see. So I
So
think you have to stop. Okay.
Slash you. Let me see.
Yeah, this is good. No, we're good.
No. Okay.
How's that?
That's good. Yeah.
Okay. All right. So thanks very much, John Lee, for the introduction, and thank you for inviting me to give this presentation. I think one of the things about the pandemic in Zoom is that we are able to do these presentations around the world and at different times during the day. So it's really great because otherwise, we'd be, I don't know, injecting a lot of carbon into the atmosphere and may not even want to come to a meeting like this. So I think the Zoom platform has been great for. I mean, the pandemic has been terrible, but this is one thing that's been good about it. We've been able to keep having conversations around the world in ways that we couldn't before. So thanks very much for inviting me. So for an overview, I'd like to start with a simple definition of water security and then talk about what satellites are telling us about water security. And this is almost entirely from GRACE, but a little bit of radar on ground subsidence. And then talk about some of the implications and emerging policy needs for water and for food and for human security. These are all interrelated. And John Lee's mentioned that we've known each other for a long time and done a lot of work together. And as I get older, I find myself, in fact, very much motivated by the GRACE data to actually try to impact solutions, impact adaptation, impact policy. And we've had some success with that. I mean, we're definitely researchers first and foremost, but I do spend a lot of time writing for the general public. There was a period of time when I was giving hundreds of lectures. A lot of it had to do with California groundwater and the misuse of California groundwater, and the fact that we could see it all with our satellites. And I just felt the need to communicate about it. So what are some of the implications, and then what are we going to do about it? And a lot of it for me has been science communication. So a simple definition of water security. I like to keep it very simple. I mean, there are some very complicated definitions out there, but I sort of scope it down to, can a region or the government of a region, the leadership of a region, provide water, a reliable supply of potable water to that region's population, both now and into the future, to do all the things that it wants to do. And all those things might be things that we see here on this slide. So grow food, irrigation, water for the environment, water for people, water to produce energy, water for economic growth. It takes a lot of water to make things and to run an economy. So, you know, can a region provide a reliable supply? That's getting very hard with climate change and changing variability and increasing frequency of flooding and drought. Potable water, so it has to be clean. We know there's tremendous amount of contamination of surface water and groundwater. We also now recognize that we don't need to use crystal clear, purest water to do everything that we use water for. We can grow crops with perhaps water that's a little bit more saline. We can use water, say, for our home plumbing for toilets. Maybe it doesn't have to be drinkable unless our dogs decide they want to drink it. We recognize now that we can use water of different qualities, and you know, both now and into the future. So in the into the future part really is with a view towards population growth and the need to grow more food and provide more water for people, and also with climate change and the increasing variability. So water security isn't something that we should take for granted. And I think a lot of people look at Canada and think, wow, like Canada has so much water. And we do, but the truth is it's quite contaminated, and climate change is hitting Canada very hard. And so Canada is melting away, and just like everywhere else, there's really no place to go and hide from it. So there's lots of work to be done on water security. And one of the things that I have really enjoyed about working with the GRACE mission, and you know, back when John Lee and I and our colleagues and students and colleagues and faculty colleagues and mentors were working on this, I don't think we had any idea back. You know, we started working on this in the late 1990s, and the first launch was in 2002. And I don't think we had any idea that, you know, 20 years later or more, we would be talking about water security and what these satellites are telling us. So it's just been a phenomenal contribution to understanding global hydrology. So let's talk a little bit about that. And you know, many of the people on the listening in today probably know a lot about GRACE, but for those who don't, the first GRACE mission was launched in 2002 and ran till the end of 2017. And then the next GRACE mission was launched in 2018. I had the good fortune to be there. I like to say that it functions like a scale in the sky, and that it's a response to the gravitational changes, the time variations and spatial temporal changes in the gravity field that result from having more water in one place and less water in another place. So the satellites actually move, they're attracted towards the places that have more water, maybe pulled down a little bit, accelerated towards that region. And so the intersatellite distance changes. And by keeping track of that, we can map out the regions of the world that are gaining or losing water mass on a monthly basis. We know that it measures the change, the total water storage, the change, the delta, we call it in hydrology, the delta S, the change in storage, not the absolute amount. It would be pretty hard to measure the absolute amount from space. And total water storage, all of the snow and the surface water and the soil moisture and the groundwater together. And if we want to split that up, then we have to do research. And I'll talk about some of that in the context of how we've used it to isolate groundwater. We know that the time scales and the spatial scales are pretty large, monthly and longer, 150,000 square kilometers and greater, although there are methods out there now to do some downscaling, both space and time. And accuracy is 1.5 centimeters equivalent water height. So basically, the way I think of it is we have to have 1.5 centimeters of water spread over this 150,000 square kilometer region or more to sort of perturb the satellites and get a reasonable estimate with low enough error that we can use it. So of course, that's pretty novel compared to other satellites that I've used. I started off my career much more focused on microwave soil moisture, and really took advantage of the opportunity to work with people like John Lee and his PhD supervisor, Clark Wilson, and all of our mentor, Byron Tapley, who were the pioneers and leaders of this GRACE mission. And both John Lee and I benefited from being able to participate in the mission and get in right at the beginning. So that's the GRACE mission, and it's been going for some time. I mentioned that it was decommissioned at the end of 2017, and actually at JPL, we actually had a wake for it. We went to a bar, and we had a few drinks to say goodbye to the first GRACE mission. But just a few months later, we were able to go out to Vandenberg Air Force Base, and I was lucky enough to be out there. I didn't take this picture. If I took this picture, I should be a professional photographer. But it was really exciting to be out there and see that, especially having done so much work with the first mission and trained a whole bunch of students and worked with a whole bunch of colleagues. And so when this thing launched, I really felt like this one is for the next generation. We look at the data in a lot of different ways. Here's some animations we did a few years ago for a news show. So we're looking at the Middle East, and we wrote a paper on this region in 2013, and this is an animation I think we did in 2014. And you can see the colors go from blue and green, which means more water, to to the orange and red, which means much less water. You can see that signal sort of spread across the upper Middle East, Syria into Turkey, down around the Arabian Peninsula. And it's these kind of things, I talked a little bit about science communication. These kind of graphics are extremely helpful. So, I mean, they're great for science, but I think this sort of thing is much more important. If we want to get water managers, if we want to get people in this region to start to talk to each other about water, these are the kind of graphics that help bring people together. And so another way we look at the data, we look at the actual time series. And so these are monthly data, so we can see the ups and downs. So wet season, dry season, wet season, dry season, but we see this overall trend here, and downward trend. And we wrote this paper in 2013, and that downward trend is still continuing. Here's the little gap in here between GRACE and GRACE FO. So the picture hasn't really improved, and I will show a slide at the end that shows, in a lot of these regions where we've written regional papers, the overall picture hasn't really improved. And so that's a real concern for me and for people who are concerned about water and water management and climate adaptation. And as you get older and you've written a bunch of papers, then you can start worrying about, are these things going to have any impact on society, and try to make that happen. So yeah, things are not improving in that part of the world. And so here's, to me, one of the greatest achievements for me in terms of hydrology. The greatest contributions, I think, of the GRACE mission is a map like this. This is a trend map. And this one was published in 2018. And so in this paper that we wrote, it's 2002 through 2017. And the colors represent the places that are gaining or losing water mass. The blues are gaining, and the reds are losing. And this is over. So these are the trends that have happened over the lifetime of almost the entire lifetime of the first GRACE mission. And so it's a pretty, on one level, it's sort of, just another global map, but on another level, there's a tremendous amount of structure here that's tied to real physical things and real physical processes. So for example, we've got the biggest signals are the ice sheets, right? Greenland and Antarctica, and they are melting away and contributing to continuously rising sea level. And of course, that's a major concern. And we've got the alpine glaciers, say along the west coast of North and South America here, that show up extremely well. So those are also melting away, impacting regional water supplies and driving up sea level rise. We've got this sort of background picture of the high latitudes and the low latitudes getting wetter and the mid latitudes getting drier. So that's a climate change related signal, as are the ice glacier and ice sheet signals. We're starting to see the extremes of flooding and drought pop up, and some of these are where I live now. And so there's this Athabasca drought in the region where I live right about here, and it's been getting wetter, although now it's starting to get drier. We had a colossal drought over the summer, so maybe when we look at this plot in a few more years, it'll be less blue and maybe start to get a little bit more red. It just depends on what's happening. But the flooding and drought is starting to appear, and these are the spots that actually move around through the years. The other spots, like the ice sheets and the glaciers, those are fixed locations, and so they don't really move, as are these aquifers. And so these are the places around the world, and there are a lot where groundwater is disappearing. And we knew some of this before Grace, but we didn't know it like we know it now. So this map has really revealed all of these different hotspots for too much water, too little water, water insecurity. And this groundwater one is one that I'll focus on a lot because in this talk, because again, it's been really a major contribution of the GRACE mission in that it's really hard to measure groundwater in these aquifers. You have to drill wells, and it's really hard to put together a big picture, whether you're talking about a state like California where I used to live, or whether you're talking about the globe. Really hard to get data internationally. It's really difficult for different countries to share their data. It's tough to get it all like at the same time and in a format that you can use it. So satellites are really important for that, and the GRACE mission has been really great for helping us kind of see underground and understand what's happening with the groundwater. So I will talk a little bit more about the groundwater work that we've done. So again, I just want to reiterate, this is a very complicated and compelling picture of the future of water. And it's one that I have worked very hard to get decision makers, politicians, elected officials, water managers to understand. And that is really, really difficult. There's a lot of competition for attention these days, and I'm working hard, but I need help from those of you who are out there participating in this Zoom lecture today. Please, we need you to pick up the ball and keep running with this after people like John Lee and I retire, and whatever it is that we're going to retire. There is, climate change models are telling us that the wet areas of the world will be getting wetter, and the dry areas of the world will be getting drier. And that's something that's being discussed in COP 26 right now. And this is an early IPCC map that shows the predictions for the end of the 21st century. Precipitation increasing in high latitudes and low latitudes in the tropics, and decreasing in between. And we started looking at these data pretty early on, maybe 5 years ago or more than 5 years ago, maybe probably after 5 years, maybe around 2014, when this trend map started to really emerge and sort of crystallize. So we started wondering about, hey, are we actually seeing this? Dry areas get drier, wet areas get wetter. And so we published a paper in 2016. In fact, we took the background in that image, in that global GRACE map, it took out the hotspots and just looked at the background. And so we do see the dry areas getting drier and the wet areas getting wetter. So that should be cause for concern for sure, because the way that water is delivered or not delivered has been to be increasing frequency of flooding where it's getting wetter, or increasing intensity and strength of drought where it's getting drier. So this certainly is a challenge for humanity. So groundwater is the water that's stored under the ground in aquifers, in these rock layers or soil layers that we see in this soil layers, rock layers that we see in this diagram. We have to pump it out, right? It's underground. It's the primary water source for over 2 billion people, about a third of the population. It provides about half the water for irrigation to grow food. In many cases, it's non-renewable, meaning, especially as we go deeper into these aquifers, we pump it out, it's not going to be replenished. It took, millions of years to accumulate, and we're burning through it in, a century. So how do we get at it with Grace? Well, we started thinking about this really before the satellite even launched, that we could do sort of a simple storage balance. When we look at change in storage in land, this could be a big river basin. It's equal to the sum of the change in the snow storage, surface water storage, soil moisture, and groundwater. So we could just rearrange that. So sort of conceptually, if Grace is going to give us this, then if we want to isolate the groundwater, we have to remove the mass signal above the groundwater. So we have to remove the snow, the surface water, the soil moisture. And easier said than done, because some of these things aren't well measured. And the data sets that we use to do these studies really depends on where we are. And so if we're trying to get data out of Syria for the Middle East paper, we have to rely a lot on remote sensing. But for the work that we've done in California and in the Colorado River Basin, which are regions where I used to live, well, we can get observations, we can get snow observations, we can get surface water observations. Soil moisture is still sort of problematic because we've only recently started getting the soil moisture data, and it's pretty coarse. So we tend to use model data for soil moisture. So let me show you how we've worked through some of these studies. So here's one that we've repeated a few times now. So this is the Central Valley in California. So here's California, western part of the United States, west coast of the United States. I used to live down here somewhere. And this green part is the Central Valley. So it's really surrounded by mountains. And the Central Valley is an incredibly productive agricultural region. I think it's the most productive agricultural region in the United States, and it's a region that uses either the most or the second most groundwater in the United States. So, how did we go and solve that equation? We want to get some snow data and some snow water equivalent data and soil moisture data and surface water data. Well, so first, a couple of steps before we go do that. Here's the Grace time series for the Sacramento-San Joaquin Basin. So it's shown here in the outline, in this black and white outline. Those are the big basins of that's where like most of the water in California is. So here's that time series, and you can see these sort of phases of drought, right? 1, 2, 3. And some pretty low points here. And this winter 2021, last winter, was the driest winter on the Grace record. But one of the things that we do to kind of do reality check, of course, when we're going to look at groundwater, we go and look at well data as well. But another thing we do is put together an independent water balance of precipitation, minus evapotranspiration, minus discharge from whatever data sets that we can get. And subtract that from the DSTT change in storage that we get from Grace. So we take the derivative of this time series and compare it to P minus ET minus Q. And that's what we see here. Here's the comparison down in the lower left. So the Grace storage change, the Grace DSTT, so the differential of figure A here, and then the water balance. So it matches pretty well. And these are our time series for soil moisture, for surface water, for snow water equivalent. Surface water we take from California reservoir system. I think we're using like 90 reservoirs, the 90 biggest reservoirs. Soil moisture we're still getting from GLDAS and NLDAS, the NASA models. And snow water equivalent we're getting from the Weather Service data assimilated product. It's a combination of snow pillows and gamma surveys and real observations, but assimilated into a model. So we're going to subtract this, the snow and the surface water, the soil moisture from the Grace total water storage anomaly. And whoops, sorry, intermission. So one of our hopes is, just before I show you the result, one of our hopes is to be able to do all of this by satellite. And so we can always be using GRACE. As long as we have a storage change mission from GRACE, we can use GRACE for delta S total. Snow, I put an ASO here. Our colleague Tom Painter has been doing some high resolution aircraft work, but in the United States and in Canada, we're looking at a future K or a KU band or L band radar mission. That's a higher priority in the decadal survey here in the United States anyway. Surface water is the SWAT mission, which last time I checked was supposed to launch in 2022. And that will measure surface water heights and inundation extent and changes by repeating those measurements. We see the changes in surface water storage over time. So we can see this sort of waxing and waning, the spreading of water over the surface seasonally and following storms. And then soil moisture, I mentioned we use SMAP, which launched in 2015. So it would be cool to be able to do a lot of this from satellite, and we're certainly moving in that direction. Okay, so here's what the latest Central Valley time series looks like. So just to underscore why this is important, it's really hard. So we're looking at storage changes across this entire green area, the Central Valley, groundwater storage changes, okay? It is really hard to put that together from models. It's hard to put it together from data. So that's the plus side. The downside is we don't get it at very high resolution. The best we can do is sort of look at some of these smaller basins. But anyway, here's the picture that emerges, and just you can see there are these three phases of drought in the GRACE time frame, 2006 to 2011. That's when we wrote our first paper in 2011 on California, and then 2011 to 2017, and the rates of decline here are about the same. And what's happening here is that farmers don't have any surface water. This is a hugely agricultural region. Farmers have sometimes zero surface water, and so they have to use groundwater. And when they use the groundwater, it disappears. But the real, here's the gap here in between GRACE and GRACE FO. We've got some recharge here, but then this one, when we actually look at these numbers, and we're just writing this up now, that rate of decline is much faster than these previous droughts, okay? So this is about 70% faster than this drought or this drought. And that's important because we're actually in California trying to do the opposite. There's the Sustainable Groundwater Management Act, which is actually trying to slow the depletion. But its implementation has been so slow that, and the drought has been so bad that the opposite is happening. That so it's not really regulated yet. So the groundwater is being pumped at a far more rapid clip. So that's not good. And when we put it into the bigger picture context, this is a chart that goes back to 1961, and it's a combination of US Geological Survey wells and the Central Valley hydrological model. So it's a groundwater model that's calibrated and ingests and uses the observations. And the GRACE time series here shown in blue. And so we're looking at cumulative groundwater depletion going back to 1961 or 62. Sorry, that's the wrong number here. So the GRACE part is 2003 to 2021, but the whole picture goes back to 1962. And the colors in the background represent whether it is very dry, the tan, dark tan, or very wet, the dark blue, or moderately wet or moderately wet or moderately dry. So we see there's this overall decline, depletion of groundwater. We see that there's a little recovery in wet periods, but much bigger decrease, groundwater losses during droughts. You also see that it seems like we're having fewer wetter periods and more dry periods. And when you look at the numbers, there's actually an acceleration of the groundwater depletion. So this time series from GRACE, is losing water at a faster rate than the long-term average. And then this last part here is really, you can see how steep that is going even faster. So we're seeing that. And so that is something we are communicating about now. So a little bit on subsidence. So this is a picture of USGS hydrogeologist Joe Poland, famous picture, standing next to a telephone pole in the San Joaquin Valley in 1977, showing where the ground used to be in 1925 and 55 and 77. So, you know, that's 30 or 40 feet of subsidence. So I like to say that subsidence is like deflation of a tire, bicycle tire or automobile car tire. So just like a tire, you know, if you put air in a tire, it supports the walls of the tire. When there's water in the ground, it supports, it pushes out on the pore spaces and keeps the matrix, the geologic matrix, the rock and soil matrix, you know, it's more swollen, right? It gives it structure. And so when you pull it out, it deflates, especially where there's clay minerals. Okay, because the clay minerals are flat, and so they have a tendency to stack up on each other, and the ground more easily flattens out. So this is an old slide. We're not currently experiencing the fastest rates, but back in this time period, these are radar images from our colleague Tom Farr, who's now was at JPL but now retired. And we're looking, hang on just a second. Yeah, we're looking at this region right here. So here's California, here's the Central Valley, and this central part here, you know, San Francisco's over here. So we're just east of San Francisco. For those of you that know the UC system, there's UC Merced. It's out here, it's a bunch of cow pastures. And anyway, it's the youngest of the UC schools. So these are radar images that show the rate in that, you know, in this region, that show the rate of subsidence. And some of it's quite significant, right? A foot, 12 inches, 14 inches, up to 18 inches. And around 2015, some of this was up to a meter per year. So, you know, all these things happen when we use too much groundwater, right? Like wells go dry, the ground sinks, it costs more money to pump the water up, you know, to pay for electricity. Streams go dry. So all these negative consequences are happening, damage to infrastructure, roads, bridges, canals, etc. So, you know, we just did a little Photoshop here to look at Joe Poland in 77 versus 2015 when I made this slide. So, you know, a lot of subsidence has happened over there. And it's, oh yeah, so we go from here to here. It's a global issue now. This is a paper that came out in 2021 that's looking at the potential for a subsidence. You can see some of these regions, excuse me, like around China and East Asia and India and here in California. So it's a big concern and something that we really need to keep an eye on because of the damage and because of, you know, California was going to build a bullet train right through the middle of the Central Valley, and like, you know, then they realized, oh my gosh, we've got subsidence that now we have to, you know, keep track of. So it's a big problem. Another thing that concerns me is that a lot of these aquifers are located in these places that are drying out. Right, so these are the dry areas that are getting drier. So that means there'll be less recharge, less replenishment of the aquifers. Excuse me. I had a student, Sasha Ritchie, wrote a paper in 2015 that showed that over half of the world's major aquifers, are shown here, are being rapidly depleted. So this is, again, all GRACE-based. Thank you. Excuse me. So yeah, over half are being rapidly depleted. And this is the kind of thing I get really concerned about, like what kind of research can someone like me do, or can we do together to try to bring more of these aquifers into sustainability? What can we do as a community? Can we work with decision makers? Can we work with water managers? Can we work with aquifer groups in these different regions? So these are things that I've written about, right? The global groundwater crisis. This is a more recent one, actually, that I wrote with Grant Ferguson here at USask earlier this spring. And these are some of the time series for those aquifers from this paper that came out in April. So big concern. Okay, let's shift to what some of the implications are and emerging policy needs, and you know what sort of things are on the horizon. Well, first of all, I think the human fingerprint on the freshwater landscape, and we think of this as the freshwater landscape, that fingerprint through climate change, through ice melting, through the changing extremes, and through water management, right? We are responsible for that. That's the dominant force. that is dictating this pattern, right? It is the dominant force that is dramatically changing patterns of water availability. And that change and the things that go along with it, like threats to water security, to food security, to national security, that's happening so much faster than people realize. By the way, here in Canada, temperature is warming at twice the global average. But as you go up north, in where I live in the prairies, it's 3 times the global average. And up north, the northern part of Canada is 4 times the global average. So like there are changes that are happening fast. And I don't think we're really prepared for it. And so that's, part of what I've been devoting this sort of last phase of my career to, is making sure people understand and working with different groups to try to come up with solutions, to try to figure out how to adapt. The climate change isn't going away. Ice isn't going to stop melting, right? We're not doing a great job on slowing down groundwater depletion. So how are we going to adapt? Well, there's important implications. First of all, is that the food producing regions, it's not drought. They're just in a state of chronic water scarcity. And that's why there's all those red spots on the GRACE map. They're using more than is available to them on an annual renewable basis, right? So they're basically borrowing against the future by using all of this groundwater, and it won't be there for future generations. So that's something for us to really think about. That also means that there are distinct classes. There's a huge accessibility problems. Distinct classes of what I call the haves and the have-nots. Meaning, do you have water? Do you not have water? Do you live in a place where the water table has dropped so low that your well has gone dry? Can you afford to dig a deeper well? Well, not when the water table is 2,500 feet deep or 1,000 meters deep. That could cost $1 million US. So this accessibility has become a big issue. Hydrogeological exploration of the world's major aquifers. I don't know how long I've been talking about this, for a long time. And basically no one is listening. We have not explored our aquifers the way that we have our oil reservoirs. And that's because we don't really value water properly. I know as a modeler, if we want to do like real 3D modeling and include the subsurface, we don't have the soil information. We don't have, hopefully, we don't have, wow, that was a powerful yawn there. We just don't have the data that we don't have the data that we need. Groundwater is a critical element of national and international water supplies. Most of our political discourse or policy discourse is about rivers. Colorado River Basin in the United States is a great example. Groundwater is an afterthought. And so that just means that it remains unmanaged. And that's one of the reasons, for example, in Arizona, in the United States, why they're now having a renewed groundwater depletion problem that they had managed for many years. But now that there's not enough water in the Colorado River Basin, more people, more farmers are using groundwater, and it's disappearing again. These regional problems require regional solutions. When you look at these maps, these spots are bigger. They cross political boundaries. So when we start to look to adaptation and solutions, it's not just country by country, okay? These are international problems that require us to use water as a vehicle for collaboration rather than conflict, because it's in our mutual interest to do so, even with our enemies. And keep in mind that all climate change mitigation and adaptation strategies benefit water security, because really water is the messenger, right? That is delivering. That's how we experience climate change. It's through the changing flooding, drought, precipitation. A lot of what we talk about is water. So what are we going to do about it? I think we need to do something, because GRACE has shown us I can't see my full screen, but Grace has shown us all these time series here, right? But the Grace follow-on is showing us that things are not improving. And so, we wrote this paper, the India paper, and so we're just looking at some papers that we wrote. We wrote it in 2009. Well, look at what's happening with the water storage there. We wrote the California paper in 2011, and I showed you what's happening there. Right, we wrote the Middle East paper in 2013. We looked at the animation that's still going on. And Colorado River Basin wrote here, and you see the decline is still happening. And in fact, there's just a shortage declared on the Colorado River Basin. I just mentioned then that we're using more groundwater, especially in the southern part of the basin, which is Arizona. So things are not improving. And some of those maps that I've showed you, the aquifer map and the global GRACE map, they're really not changing. They look almost exactly the same. So there is an urgent need for regional and global science, okay, for engineering innovations, for policy innovations, okay, for social science innovations. We have to really get on this. We know it's happening, and so we need to sort of become more interdisciplinary. And I use the term transdisciplinary, which means going outside of academics and working with policymakers and water managers and city managers and so on. So we do need to do that. We need to engage more broadly with planners, stakeholders, and the public to discuss these adaptation strategies, the science needs, the policy needs. We need to co-develop questions. I think there's an urgency to climate change and to the water side of climate change that I've been talking about today that precludes us staying in our offices and just writing our next paper. If we want to make a difference, we have to do this. We have to collaborate more. We have to co-develop. Of course, we have to do the highest quality work. So I'm not saying like we don't do that. We have to do that. But I think many of us, especially as we get older, and we've have tenure, we've written our papers, we have an obligation to get out there and do this work and to communicate to stakeholders and to resource managers and elected officials and to the public. So this is the transdisciplinary part. We really need to go outside of our academic walls. And to me, if we're going to have an impact, that's the way that we're going to do it. Otherwise, we're basically talking to ourselves. So, some positive notes. In 2014, California passed the Sustainable Groundwater Management Act. We don't have to read all this, but they're finally managing groundwater and trying to minimize falling water tables and loss of groundwater and declining groundwater storage and subsidence and all the things that we talked about. The negative is it's taking 27 years to implement. So until 2042 to fully implement it. And I showed you what's happening. Groundwater depletion is accelerating. So, my concern is that there'll be nothing left to manage by the time SGMA, the Sustainable Groundwater Management Act, is enacted. But at least it happened, and there's some hope for the future. There's global groups that are getting together and working on groundwater. Here's one from meeting before COVID. We started getting going on a global groundwater sustainability call to action, and then COVID hit. And so, we've just done a few things online and just kind of waiting to get back on it. But this is this idea of sort of, thinking about where scientists can come together with planners and water managers in these different regions around the world and, have sort of a big picture of what can we do globally, but also individually, what can we do in some of these aquifers, for example, in that map from Sasha Ritchie that I showed you. So I will end it here. And just some links here. A lot of what I talked about is in an easy reading piece called A Map of the Future of Water, and it's in a magazine called Trend magazine. And here's the link here, trend.pewtrust.org. Here is our institute, the Global Institute for Water Security, where I work. So it's water.usas.ca. Always looking for new Twitter followers. So please, at least one would be good. From today's meeting, I see that there's 280 or so people. So hopefully I get one new Twitter follower. And, I talk a lot about communication. And so 3 years ago, so this is the third season I've been doing a podcast. It was called Let's Talk About Water. Now we call it What About Water? Just had a name change for sort of, we didn't actually own the Let's Talk About Water name. So anyway, you know, we've had some really good guests and we've talked about some really important issues. And it is a way to, you know, it's just another vehicle for communication. It's very science-based. I have a lot of colleagues that use it in their classes, especially during COVID. They will ask their students, you know, for homework assignment, hey, go listen to, you know, this conversation that, you know, Jay had with Hank Ovink, who's the water ambassador for the Netherlands. So go listen to this conversation that he had with, you know, this indigenous a woman living in Arizona who talked about all of the issues about accessibility to water. So please, I encourage you to go have a look at that and the website. It's on all the usual podcast platforms and just whataboutwater.org. And I think that's it. So happy to answer any questions. Thank you very much for listening.
Okay, Jay, thank you so much. Okay, so you can keep this. Oh yeah, this one. Yeah,
Okay.
we can go back. Yeah.
Yes, we can.
Any related question? Yeah. Okay, so now we have at least 10 to 15 minutes for questions. So people, if I know we have a very big audience. If you want to speak directly, you can just unmute your microphone, or you can. Another option is type in the chat room if you have any questions.
And John Lee, if you want to, you moderate the questions. I'll get too distracted if I have to look at all the chat stuff. So you can just ask me whatever.
Okay, we already had one question here. My concern is about the consistency between GRIS and GRIS follow-on. Do you have any comment?
Yeah, so I think there's been a fair amount of work that's been done looking at that consistency, and I think that most people are pretty satisfied. You can see a little bit of jump in the data. We try to not overinterpret what's happened in that gap, but so far so good. I think I don't know about you, John Lee, but I haven't really seen anything too negative.
You are more optimistic than I am. But I think it's okay, right now for GRIS follow-on. But in general, it's not as what we expected before the launch.
Yeah. So how do you mean? So what did you expect?
I think we, with newer generation of hardware, with all the experiences we accumulated, we expect, at least I expect to see, the kind of minimum increase of the accuracy. But right now, I think the GRIS follow-on, if we compare with the whole GRIS mission, they are comparable.
Yes.
But not as good as the middle part.
Okay.
If you look at the best portion, the middle after 2003 to I think 2010, 2011, or even 2012, GRIS follow-on is not as good as GRIS.
Yeah, that's too bad, and also too bad that the accuracy isn't as good. Just keep our fingers crossed for the future and the next.
Yeah, we have to rely on next, GRIS mission.
Right.
But the good thing is the continuity. We are going to have a much longer, record of GRIS data.
And so that's the thing, at least for me, that's the thing that, and we are calling this a climate continuation mission, right? I mean, that's sort of the class of missions that the GRIS follow-on is in. And so for me, that's really important, having that continuity, being able to look at these long time series and, seeing that they match up pretty well. They're not really, they're what we're seeing now with the places that we've looked is what we're seeing before, just the continuity.
Yeah, I think GRIS follow-on itself is fine, but the only issue is the hardware, for the single accelerometer. There's no way we can get rid of it right now.
Yeah. Okay.
So another question, Jay, thank you for your presentation. I want to focus on the joint study of water resources by satellite altimetry and the GRACE follow-on. Are there any good suggestions? Yeah, that's a good question.
Yeah, so I think for the most part, we have underutilized the opportunity to combine altimetry, GPS, radar, and GRACE. So I think the best work is, probably come out on the ocean side, looking at sea level and thermal expansion, and less so on the water side. Early on, there were some people that were looking at the Amazon, some of the big river basins, and looking at floodplain storage and using altimetry to get at floodplain storage, and then comparing that to GRACE and trying to pull off, kind of like we do with groundwater, but just trying to pull off what's the floodplain signal. And that's really interesting, but for the most part, I think it's really underutilized.
Yeah, I agree with you. Yeah, I think for the joint study, another likely, candidate is the large lakes, for the Caspian Sea, also some other, lakes.
Yeah.
Okay, let's see. So you can read the chat room, right? There's one more. Do you have any comments on GRACE follow-on contribution to extreme hydrological change?
I'm sorry, I'll just let you read the question. See, this is
Do
the
you
problem.
have any
I
comments
see it.
on
I
GRACE
see it. Do you have any comments on GRACE FO contribution to extreme hydrological change? Yes, I do. I think so. One of the problems with the extremes is that they happen faster than we can really kind of get the GRACE data. So, there's great potential for regional drought and regional flooding. And I think it gives us a different and probably more holistic view of what's happening, say, compared to these drought indices that are just using soil moisture. So I think there's a lot of potential there. We've done a few drought things, and early on, JT Rager did some flood stuff. Again, I think it's underutilized, and there's always this latency, right? The data are so far behind. Availability of the data lag, so many months that it's not really useful for like monitoring. I find it more useful for historical studies, like really understanding what happened in the past.
Yeah, there's one more question. You probably need to go back to the slide. There's a big
red area of negative storage change in eastern Tibet plateau inside China, not the one in India. Okay, let's go back and let's take a look. You can kind of see it there. Let's get a real map. Hold on. That's good. Good enough. In here.
Yeah.
Okay.
Here.
So this is groundwater. This is Bangladesh. So where are we talking about in here?
Eastern. Yeah. Eastern. Yeah.
So part of this is Bangladesh, right in here. This is Bangladesh. I can't really see this so well. I don't actually know what it is. So good, excellent question. That's an area, we have not turned over. We haven't looked under every rock. So I don't actually know what's going on there. So that would be a nice study for somebody who's listening in. Another one that we haven't really, and I should really tackle this, is this one up here. And this one is important because there's like a tremendous amount of water that's being used for the tar sands, for oil sands production. But at the same time, there's post-glacial rebound there and it's not well quantified. And there was a drought. So we don't really know very well what's happening here. So this is a good one. I know this part here, like we've looked at it, been to Bangladesh, I know what's going on there. And there's a tremendous amount of groundwater depletion. Here, I don't know.
Yeah, I think that one, you remember there's a parallel paper, Matt published a 2009 Nature paper for the Northwest India. At the same time, GRL published another paper, I forgot the first name, the
Yeah,
first
yeah.
author. Last name.
Tawari,
Yeah,
right, right.
yeah, Tawari. I
Yeah.
think in their paper, they try to interpret the signal on the east side,
Oh, okay, good.
the groundwater still as a groundwater, storage change.
Yes,
And
and I
I
remember that one. They also did a lot of like looking at the glaciers and maybe pulled out the glacial melts. They removed that from the signal.
yeah. I personally believe that's a combination of glacial melting and
Yeah. So that's
groundwater.
yeah, right.
Yeah, plus
I
maybe
remember
some,
that.
drought in
Yep.
southwest China. Yeah.
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 Okay.
Okay, let me see. I think the next one is Gao Hong. Yeah, Gao Hong's question. Great,
This one,
thanks.
great. Thanks for the talk.
Yeah, you go ahead. Yeah.
Yeah, climate change, water security is happening. Hydrologists accept warning of society, government of it with our research work. Is there any other thing we can do to make a contribution? I think the best things that we can do are that we keep doing our work, that sometimes it's important to help get the message out by maybe writing a simple, sometimes in Canada and the US, we call them policy briefs, some kind of translation, easy piece of like for a science magazine or for a science blog or something like that. Anything that you can do to help people understand, because like our work is so complicated, the people that need to know can't understand what we're talking about in our papers, and they're not going to go pick up, whatever Journal of Geodesy or Journal of Glaciology or Water Resources Research. So that kind of falls to us to write it in more accessible formats. And there are lots of like science blogs and things that you can do that you work on that can be extremely helpful. The other thing I used to do a lot of, less so here in Canada, but I used to give a lot of public lectures. So I did mention at the beginning of the call, John Lee, when we first started talking, that I just went and taught a 9th grade class. I'd never miss an opportunity to go and talk to people at schools. So I have given a lot of public lectures, especially when I was in the United States. I'm not as well known over here in Canada. So I don't have as many opportunities, but anything like that you could do, I would give them at churches, I would give them at like senior citizens' homes, just anyone who asked, I would go give a talk. So whatever you can do there, we have to help the general public understand. Some people these days are doing more with art, which is great. Whatever it is that works for you, there are ways to, another thing that our colleague Catherine Hayhoe does a lot of work on science communication, climate communication. She'll say, just talk, just have conversations, talk to your neighbors, talk to your family, just talk about it, get people thinking about it.
Yeah, I want to make a comment here. We all know Jay is a very, successful scientist, very, productive, outstanding scientist. Actually, what I admire him the most is not, the papers he published. Actually, it's his engagement, to the community. Over the years, just like, Jay said, he made a lot of public speeches, presentations. I'm not sure how many of the audience, knew that, Jay was a movie star. Yeah. You want to talk about the movie? Yeah. The
Well,
motivation.
so that's just another way. So thank you very much, John Lee, for those kind comments. I really appreciate it. Yeah, so that's just another form of science communication, is to, when I was younger and people would say, hey, you want to do like a news thing or something, be on a newscast or talk about your work, I would just be so scared. I would say, no, I can't do it. But I don't know, as I got older, I got more comfortable with it. But anyway, I have had the opportunity to be in a few documentaries. And They can be very powerful. Again, it's not, we can write all the papers that we want. We can write 300 papers. We can have, an H index that's whatever, 150. That doesn't mean we're going to have any impact on society. So I have had those opportunities. Part of it was that, I was in California, close to the movie making, industry, and I was doing that work at the same time. So it was kind of, I was easy for those producers to get. I was right there, and I was doing this work. But I do think it's really important. So I have enjoyed doing that, but much less now. Of course, I'm up in Canada. It's, buried in the snow, and we have different problems here.
Okay, thanks. Yeah, let me see. We still have quite some question here. Let me see the next one. Gao Hong's one. So Huang Ziyong, for the next presentation, I'm interested in drought monitoring using GRACE data. Up till now, many GRACE-based drought indices were developed. How does U.S. government? Yeah.
So that's so our colleague Matt Rodell. Matt was my student at University of Texas. He was the first guy that that worked for me that worked on GRACE, and so he is the director of the Hydrological Sciences Lab at the Goddard Space Flight Center, and so he works with the National Drought Monitor to integrate GRACE into the Drought Monitor. And so it's actually being integrated into at least one of the drought monitoring products. And so, it's worth taking a look at. That's one of the things I think that the GRACE mission, NASA people and Byron Tapley have been very proud of, to say, like, yeah, it's in the US Drought Monitor. So it is used there. I don't know that it's used more broadly. I think a lot of it is much more on the research end. But that is one success story, is that integration into the US Drought Monitor. Okay, here's one on the water transfer project, south to north water transfer project. How about it in China? Actually improve the groundwater in North China Plain. Can we see signal improvement from GRACE? I haven't looked yet. But let's say this, that if it does improve it, if it either helps replenish it or it helps to slow the rate of depletion, we'll see it, right?
Yeah, you're right.
It may take a while.
Yeah. There are a few papers published, discussing the improvement. No signal is good signal, because in the Northern China Plain, people expect to see groundwater depletion due to the agriculture, pumping. Yeah. But in recent years, we don't see a very, bad situation. Actually, the groundwater is stabilizing.
Yeah. So that's what would be great for California, right? But I don't even know if they're going to try to head that way.
Yeah, that has been attributed to the water transfer project.
Yeah, that's good. We've seen some small scale, so nothing to GRACE, like in Arizona, there's been some recharge of some managed aquifer recharge and some recharge of the aquifers, but it's very, very small, nothing you'd ever see on GRACE.
It can be seen clearly. Probably let's go to the next one. Shaoxingmo. You mentioned the mid-latitude trend to become drier. That's interesting. Could you talk more about it? What's the major cause?
Yeah, so I think that's a climate. I mean, it's basically been attributed to, the IPCC model suggests that this is going to be happening. It has to do with the changing precipitation patterns that, and so I showed that figure, and we are starting to see it in the GRACE data. One of the things that complicates it, though, although precipitation is increasing at high latitudes, at the same time the ice is melting. So, how that, and that's probably not as well captured in our climate models. And so that balance between the permafrost thawing and melting and the snow melting and the greater precipitation, it's not clear over time how that's going to play out. But we do, so we'll probably have to kind of disaggregate the signal and try to understand, just like we've done with the groundwater, how much of this is precipitation change, what's happening with permafrost thaw, where's that water going, what's happening with changing snow water equivalent. So, and our precip data is much better at lower latitudes, so it's going to be easier to understand what's happening at lower latitudes and mid latitudes. But once we get up to the high latitudes, it's harder.
Okay, let's see. I think just some
So Liang has his hand up.
I think.
Yeah, did you want to ask a question?
Yes, I have to. Sorry, I just have to unmute myself. Yeah, thank you, Jane, for wonderful talk. Every time I listening to a talk, I learn a lot. Always
thank you.
Insightful, informative, and stimulating. I do have a few. I know it's getting late on your side. Just two quick questions. The one is when you talk about the using GRIS to monitor the droughts and the depletions, groundwater. Also, here's good news. We were inspired by your work, so we have been actually assimilating GRIS along with other like a microwave-derived satellite like soil moisture information into a landscape model for to revisit the 2011 drought in Texas. You know, that's a drought record, a single one-year drought record.
Oh, that's right, right.
So we found the when you assimilate both MODIS and AMSA soil moisture into a land model, the drought will be more severe than which was detected by U.S. Drought Monitor in 2011. So when TWDB, Texas Water Development Board, saw that result, they approached to us. They wanted us to give a talk next week. Actually, I know we've been when Robert Mace was with TWDB, we've been working with him, and he had a long conversation with Matt Rodell and with you. But Robert Mace now left. They have some other new leaders in TWDB. So now they are interested in climate change.
Oh, very good.
Like a GRIS kind of thing. So
that's really good.
Yeah, I'm sure you will be pleased to hear that. So we're going to meet with them next week.
Oh, excellent.
If you have anything specifically want me to pass on, I'm happy to.
No, I can't think of anything, but that's really good. And, let me know how, like, the kind of work that you're doing with them. It's just really good to be able to share those stories.
Yeah, I mean, I know this is especially to deal with agency water management people at a local, state or local level. It's even though from research point of view, we know what we do is really useful, meaningful, but how to use that information to manage water and for decision making, I really agree with you. We need to work together. And
so that's really great, Liang. Thank you for letting me know about that.
Yeah, I'll keep you updated, both of you, and thank you for thank you, Jenny, for organizing this. I'll keep you
you're welcome.
About this. Yeah, another short one is you just talk about climate models may still have limitations in modeling, like permafrost, human water management. So could you just recommend how, like a young scientist, many of them in this audience, to put their effort in maybe next few years, next 5-10 years, to focus on in terms of model development? What we must do to improve our model?
Yeah, so I mean, you know this better than I do, Liang. So maybe you should maybe
no, you know
you should tell the crowd. But one of the things I mentioned it a little bit. I mean, one of the things I'm really interested in or concerned about is the data, is the availability of the data. So like the soil depth data over large areas, right? The characterization of getting three-dimensional aquifer data into, even in a simple way, into land surface models like yours. So the data side, I think, is really important. There's a lot of things that we don't know. The topography under rivers, right? The hydrography, the topography under lakes. If we want to put all that stuff into our models, we have to start working on compiling those data sets. But then the things, so let me I'll just give you a little Canadian focus here. I mentioned that things are melting away very quickly here, and they are. And so the permafrost is melting very quickly. And what happens to that permafrost? Where does the water go, right? How does it change the active layer? The strength of the water cycle. How, of course, there's all the greenhouse gas release, but I'm just thinking about the physical hydrology. As we know, and we're seeing it now in a big way, as the permafrost melts, the ground is, the geomorphology is changing. And it's not that we can get that into our models, but I think we have to get parts of it into the models, right? Like, how can we predict how a perched surface water environment in a frozen part of Canada, or the frozen north, it doesn't have to be Canada, what happens to that water? And can we capture that realistically? If the permafrost melts, does the lake sink into the ground? Where does that water go, right? Does the surface water environment become more of a groundwater environment? How much of that ends up in our rivers? So I think those things are really important. Another thing, I think, just thinking about water and in climate models, and maybe this is more integrated assessment models, but I think it's really hard to predict the future. It's hard to predict human decision making. And so what happens to water sometimes is really dependent on some of the policy decisions, right? So, this north to south transfer, like, can you capture that in a model? But what happens, with the Sustainable Groundwater Management Act in California? What's going to, we don't know what's going to happen. Are farmers going to start switching crops, right? That sort of stuff, like these adaptation things that we're going to do, those are really hard to predict. And in some sense, that's kind of like a big data problem, like understanding human behavior, big data analysis, right? And then maybe, bring that sort of parameterization into a climate model. Just a few thoughts.
Yeah, thank you, Jay.
Sure.
Oh, okay, good.
Very good. Yeah. Really
So
appreciate
I'm just curious. It's only your graphic has been shaking. So you
My
are
computer?
sitting. What are you
So-
using? You are sitting or standing somewhere?
Oh, really?
Yeah, sometimes very
Sometimes.
shaky.
Maybe I'm excited to hear, Jay.
Okay. Okay. Anyway, okay. I think there's one more question. Hopefully that's the last one. We already 20 minutes past 9. So from Shongyun. So Jay, you say?
Let me take a look. Is it down the bottom? You mentioned clay minerals.
Yeah.
Is this prerequisite for land subsidence? Yeah, it is. So the clay mineral, and the only way to know is to, ask your local geology survey, look for geologic maps. But the reason is that the clay minerals are flat. Like if they were rounded minerals, the subsidence is going to be less. Like you can maintain the structural integrity more if the minerals are a little bit more rounded. Once they're flat, it's kind of like a deck of cards. Like if you take a deck of cards or like a stack of dishes in the sink, right? You take a deck of cards, they're flat, they can get really flat, right? They might be all messed up, but if somehow they get organized, they get really flat. Same thing with dishes in the sink. Maybe you throw them in there and they're all messy and they take up a lot of space, but at some point, for some process is going to help them get organized and flatten out. That's what happens with the clay minerals. The only way to really know is to look at geologic maps.
Okay, thank you. Yeah, I think
And
probably.
by the way,
Yeah.
by the way, I had that slide. There was a paper on like the global potential for that was in Science at the beginning of the year on the global potential for subsidence. And I think that is largely based on geologic maps that show how much clay is in the aquifers.
Okay, thank you for the explanation. Let me see, there's another one. Could you please comment the role of observation precipitable water vapor in the study of groundwater? The role of observation precipitable water vapor.
Well, okay. So the only connection I can think of there is when we are thinking about how much rain happens in a certain region, we really need to understand the vapor transport, right? The precipitation, the vapor transport in and out of that region. And so as that changes, then the rainfall changes, the potential for recharge changes. Precipitable water, I haven't followed it in a few years, but it's a tough thing to me. Water vapor is a tough thing to do remotely using remote sensing.
Okay, thank you, Jay. I think probably we have to stop. It's already 9:21. Let's thank Jay again for the wonderful presentation. Also, I really appreciate your support to this online forum.
My pleasure.
Hopefully, sometime in the future I will come back to you, for help again,
Yes.
down the road.
Sure.
Okay.
Absolutely
thank
happy
you.
to help. I love, like I said, I don't get to go in the classroom much anymore, so this is a lot of fun for me. And also, John Lee, let's make sure we talk about planning some kind of a meeting up in Canada.
That's Banff. Definitely, this is something we want to do. Yeah.
Yeah. So we have
Also,
to get
I do
Leon
have
involved
another
in the
plan for
planning.
you. I've been
You
thinking
do.
about to invite you to China for, we have been organizing a summer school in China.
Yeah, that would be great.
Hopefully, in the future.
Yes,
hopefully you can help
sometime when we're traveling again. Yeah, that would be great.
Okay. Okay, thank you again. Okay, bye-bye.